Thank you. Yeah, so my name's Evan Gilman, and this is Doug Barth. And we're both SREs, which originally met at PagerDuty, where we worked some years ago. How many? Like 5 years ago or something like that.
Yep.
And Doug hails from a software engineering background, while I'm coming with a background in computer networks. Right now, Doug's an SRE at Stripe, and I've been working on a FOSS project called Spiffy, which actually aims to solve some of the problems we'll discuss today. So we gave another talk in LISA 2016. Some of you may have seen it, which kind of dove deep into like architectural diagrams and things like that on how to actually build systems which adhere to the zero trust model. But I got some feedback that it went pretty deep pretty quickly. So I wanted to take this time today to kind of pull back a little bit and talk more about kind of high level how we got to where we are today, what zero trust means, what it encompasses, and kind of just for lack of better words, the ethos around this whole ecosystem. So with that, we'll start talking about kind of how Doug and I got into this zero trust business and why. And in order to do that, we really kind of have to talk about the work that we did together at PagerDuty. So we both joined PagerDuty within a couple months of each other, and when we joined, it was still pretty young. It was a handful of folks and a very small infrastructure. But in order to understand kind of why we did what we did there, it's useful to understand kind of the PagerDuty business needs and infrastructure needs. So PagerDuty, as I'm sure everyone knows here, is an incident response orchestration platform, which is intended to minimize downtime for its customers, which essentially means that it has to be up when you're down, right? So reliability is a really, really core principle to the PagerDuty business. And in order to meet those availability goals, PagerDuty is hosted in multiple providers and regions, right? And each one of these dotted lines on the screen here represents a geographically disparate provider or region. And because of this, even though the infrastructure is small, but because of this active, regional architecture, operating it was quite challenging still. So all these, as I mentioned, all these clusters are active, and there are a lot of third-party networks between each of these regions. There wasn't like private transport or anything like that. Most of these flows are going over open internet, which presents a pretty large security challenge because we wanted to provide, access control and confidentiality for these things, but because of the architecture, you have to do it for the majority of flows because 9 times out of 10 the flow is traversing the internet. And so in order to kind of address some of these challenges, we kind of have to bite off small chunks because there was a lot to work on. And at the time when we were so small, a lot of this stuff was just done by hand, and case-by-case basis kind of thing, which was rapidly becoming untenable, especially as PagerDuty grew. So we chose to kind of tackle the access control problem first. And essentially what we really wanted was just kind of like AWS security groups. I'm glad you're probably familiar with how those work. The only problem is that security groups are AWS specific, and furthermore they're region specific even within AWS. So using security groups as is was kind of a non-starter for us. Just didn't work very well. So we needed the same functionality that security groups provides, but we needed it like cross-cloud and cross-region. So in order to do that, we built a whole bunch of kind of heavyweight automation of IP tables into Chef, which is a configuration management that we were using at the time. And the stuff that we built into Chef provided this security group-like semantics without actual security groups. But in order to do that, we wrote what's called a Chef LWRP, which is essentially like a custom declaration within the Chef DSL. And then Chef, we would declare this policy in line with Chef recipes for our applications, and Chef would chew on these policies and translate those under the covers into IP table rules. So here's an example of what that DSL looked like for us. And this DSL would be executed on a web server in order to allow access from a load balancer, right? So underneath the covers, we would say, okay, what are all the load balancers? What are the IP addresses? All right, like configure IP tables, do all that stuff. But this high-level interface was very useful for us and got us basically most of the flexibility we needed, that kind of security group-like feeling, So with this access control problem mostly solved, we wanted to turn to this privacy issue. So like IP tables at the time, all the encryption we would do like on a case-by-case basis by hand, and it was really bad. Like trying to jam S-tunnel between like Cassandra nodes in the same cluster or Zookeeper nodes in the same cluster is really not a fun time. And there's a lot of these things don't support natively TLS or any kind of privacy at all, right? So securing those kinds of flows, active across the internet, was challenging, to say the least. So what we really wanted was this kind of like blanket encryption that was just easy to use and just worked, and we wouldn't have to like tune all these knobs on these applications all over the place and identify where we need to put it and so on and so forth. And this is a challenge a lot of people face today, and the most popular solution here is to turn up VPN. Usually like site-to-site kind of VPN tunnels, right? But for PagerDuty architecture, these site-to-site VPN tunnels pose a lot of challenges. Mainly because of this active-active stuff, there's a lot of cross-DC talk, right? Like most of the traffic in PagerDuty infrastructure is traversing the internet, which ends up meaning that these tunnels will be really, really heavily utilized, right? Which brings availability concerns. What happens if one goes down? It brings scalability concerns as we scale up and out. What does that mean for having to scale these VPN heads? And then you have to do all kinds of nasty stuff like equal cost multipath and all these other things in order to make stuff work the way that it should work. Additionally, not all the providers have this VPC-like functionality like AWS has. And some completely lack private network, lack any kind of network controls over routing tables or anything like that. And those particular providers would force this VPN site-to-site model into like this hub and spoke architecture. And I put an example down here at the bottom. So without any kind of control to route traffic through these VPN heads, like each node would actually have to dial into the local VPN head and to get routed out to other sites. So you can see that like all these things combined give this more typical approach of VPN a lot of overhead for us, and a lot of concern. So we weren't super happy about that. And additionally, kind of the funny thing is like we didn't really care about this routing architecture at all. All we wanted was the privacy that the VPN normally gives us, you know. So what we did was we decided to drop the VPN bit and kind of just keep this IPsec part. So what that means is that we ended up deploying like raw IPsec layers in a mode called transport mode, which means there is no tunnel. The IPsec security is applied directly to the layer 3 payload, and there's no IP and IP or anything like that. And we configured it as a full opportunistic mesh. So the network goes from looking, you know, something like this with the regular site-to-site VPN approach, more to something like this, right? Where mutual authentication occurs as soon as the first packet is sent, and then encryption gets applied transparently from then on. This encryption is occurring at the kernel level, so the application has no idea that this is happening. It's all installed as policy into the kernel, and it kind of just works. And additionally, the kernel is configured to drop all packets which are not part of an associated IPsec session. So it's basically impossible to send or receive packet up into kind of user land that does not have an active IPsec association applied to it. So with this kind of approach, we got all the benefits that you would normally get with VPN in terms of privacy, without the VPN itself, a separate address space, and all this other stuff that comes with management of an overlay network. So we got all this confidentiality using IPsec, and we got additionally access control using IP tables, and to some extent IPsec too, because you could not even enter this network without successful crypto negotiation, turn up IPsec. So when you put these things together, there's this IP tables automation and this like full mesh IPsec transport stuff. The system begins to exhibit some interesting properties. So the first is that we can pretty much assert that all flows are authenticated and encrypted, right? And we know that because we can audit kernel configuration and we can assert, yes, like this kernel is not shipping any packets which are not part of IPsec association. We can also kind of assert that all flows are authorized because we've checked all this policy into code. The chef stuff runs all the time, like constantly enforcing this policy into IP tables. So there was kind of really strong visibility and assertion there. And furthermore, there's no inherent value in IP address because we kind of took all these things, leveled them up into this logical software domain. What it ended up meaning is we could turn up compute pretty much anywhere in the world without having to worry about was it on the right network, what source IP is it coming from, yada, 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 because all of this stuff, all the kind of enforcement under the covers that we were building was all fully automated. So we could turn up new subnets and new data centers really, really easily, which was kind of cool. But perhaps the most interesting of all these properties is that the network has no centralized firewall, right? No network gateways that you'd have to pin traffic through in order to reach one site or another site, right? And there was no private network. There was, no like kind of safe zone or anything like that. So essentially, we had succeeded in building this secure perimeterless network across multiple cloud providers, right? Which was not, our initial intention to build perimeterless. It's just kind of due to the needs and the way things went. That's just kind of where we ended up. So it was around this time that the BeyondCorp paper was published, the first one at least. And this described Google's corporate network and their move to perimeterless on their corporate network. And they had been working on this project for a number of years by the time the paper was eventually released. And as I mentioned, there's been a series of papers since then. I think there's actually 5 of them now or something like that. But these papers basically describe this unmanageable perimeter at Google corporate campuses, right? And worldwide, they have a huge corporate network. And it had grown just way too large and way too permeable. Remote work is very, very common. People are coming in and out, visitors, all this kind of stuff. Like having a perimeter on the corporate network began to make less and less sense. Furthermore, because of this permeability, it was pretty much ineffective at stopping all the modern threats, right? As soon as somebody's laptop got owned, the gig is up. They're inside the network, and that's it. So this was a really exciting paper for us to read because there are a lot of similar principles applied between Google's approaches in building BeyondCorp and the approaches that we had taken, solving similar challenges inside the data center. And it validated kind of a lot of our early decisions at PagerDuty, which was kind of nice to read about. And it not only validated these early decisions, but it kind of also exposed to us this additional use case, which is this client-side use case. We had been building similar networks inside the data center. They were building these kinds of networks on, client-to-server access, which is kind of a different beast in and of itself. Reading that, you start to realize this is really like a broader application of the same philosophies we were using inside the data center. And it helped us to understand kind of like the full scope and implications of this model, which we now call the zero trust model. So Doug and I kind of thought this was interesting, and we said, look, there's something bigger here than just this cool perimeterless thing we built in the cloud. And so we gave a pair of talks on the model and its reasoning and how we came about it. And shortly thereafter, we had an opportunity to write a book on it. And it was kind of amusing because neither Doug nor I really appreciate or like to write. But we were happy to do it because, at the time we were talking about this stuff, there was very little material publicly available on how to build these kinds of networks. So, we were happy to do that. And so with that, I'd like to take up Doug. He's going to come up and talk about the model itself.
All right. Thank you. Can you guys hear me in the back? Yep. All right. So we're going to talk about kind of where we ended up in the course of writing this book, what's like the philosophies and the high-level concepts you should take away from what it means to build a zero-trust network. And I think the first place to really start here is at what type of threat are we expecting inside of these types of networks. And in a zero-trust network, we are making the explicit declaration that our internal network is as untrustworthy as a public network would be. And so if we don't trust our internal network, like we don't trust, say, the internet, our posture inside that network is very different. And ultimately what that ends up meaning is we're going to remove trust from the network itself, and we need to bring it back to endpoints in the system. So if we have no trust in the network, what does that end up meaning for us? That means that your position, your IP address inside that network is not a valid way to actually do authentication or authorization, which is how we tend to handle that today in perimeter architectures. And instead, what we want to move towards is authenticating 3 separate entities on the network: users, devices, and applications. But it gets a little deeper there, and we'll get to that later because there's a subtle distinction between authenticating versus authorization in this network. Another thing that we want to make sure that we do when we remove trust from this network is we very much do not want to just rebuild a logical perimeter network and declare it zero trust because we use different terms. So another kind of key concept is that inside these network designs, you tend to see very, very rigorous least privilege being pushed throughout the network. And that kind of varies based on companies. So in someone who's say running inside AWS, that usually takes the form of very fine-grained security group definitions on every single host. in maybe a physical data center that might be turning up host-based firewalls to do the same concept. But really like making sure that your entire network architecture is fine-grained and very rigorous in describing its connectivity. And so like the way I tend to like kind of take a step back and think about that is instead of having a large like perimeter firewall where we do all of our enforcement, we're going to turn that idea on its head, and we're going to have many small like firewalls, or maybe a better term would be like control devices, just sprinkled throughout the network. And we're going to treat this thing like a big distributed system, which it actually is, right? And we're going to have automation go through and automatically reconfigure those based on changes inside the system. So inside a zero trust network, we want to expect, or we require that every flow is expected. And when we say this, what we're really meaning is that we have mechanisms in place to authenticate and authorize every single connection inside that network. And in general, if you have not authenticated and been authorized to communicate, then we will drop traffic. It's not always the case. Like you still have scenarios where people aren't like fully authenticated. A great example here is single sign-on for a user. Obviously, we have to like not just drop their request, we have to send them somewhere to authenticate themselves. But even laptops or endpoints would have a similar setup, right, where you want to model out how do I go about bringing this device through a bootstrapping phase to get it to a point where now it can communicate more widely in the network. And so when we like do these authorization decisions, we need some policy somewhere that tells us what is and is not allowed. And this is kind of like the key asset that you're building when you're creating a zero trust network. You're really just making this big database of flows and communication patterns that you're supposed to allow. And if we're going to like invest in that database, one like kind of key idea we see in people that build these networks is that they purposely build policy that's completely divorced from the physical implementation of the network. And so a term that we like to use for that is intent-based policy. So instead of giving people tools where they describe this subnet can or cannot talk to that subnet, what you actually would prefer to capture is this service, this like very fine-grained workload-based system is allowed to talk to this other system. And from that like intent-based policy, you're going to put automation in your network that'll go and calculate, okay, well, this workload is running on these servers. Those servers have these IPs. So therefore, our enforcement mechanism should be XYZ, right? And if we change it tomorrow, we already have the automation in place to reconfigure the network. Fairly simple idea, right? We're basically treating like the policy as like this logical system, but often sometimes we like kind of don't introduce that layer of abstraction, but I think it's valuable over time. An interesting thing is when you like look at different companies that do this, there's like a tendency towards like describing what's called a domain-specific language to define these policies, but it's not really required. In PagerDuty's case, Evan showed chef automation that was very declarative and said like application allows connections from the load balancer. Google, similarly for their access proxy, gave their engineering teams policy languages that they could define, like my service allows access from X employees on such and such devices, and then they'd like shove it into the access proxy, and the access proxy was actually like figuring out whether or not that connection should be allowed. But while like DSLs have like a really nice property that it sets up a good workflow for you to make or propose changes to it, review them, ultimately deploy them, I don't think it's like required that it be DSL based. You could imagine a management console where people go in and like fill out a database essentially that's still intent based, and there's automation behind the scenes doing the work. Perhaps a good example of that is, again, bringing it back to infrastructure we know about. Amazon security groups, in a lot of ways, are intent-based policy inside a network environment. You don't make allowances that say these IPs or these subnets can communicate with each other, although you are able to do that. Instead, you tend to write security groups where you say, all right, every like application server has the application server security group, load balancers have the load balancer security group, and there's an allowance in the application security group that says the load balancer security group gets access to my infrastructure. But if you like dig under the covers, what is Amazon actually doing for you? it's just IP tables. They're just like reconfiguring their host systems to decide whether or not you can have access. And that's why you ultimately end up seeing like limits on how many rules you can have and things like that. They're just managing like the scaling characteristics of this very simple idea, just applied like at an abstraction below you. The next like kind of big thing that we want to like socialize and get people thinking about is the Beyond Court papers talked a lot about the importance of considering like the entire security context when you're making a decision on whether or not you should allow someone to communicate in a network. And so they identified that user, device, and application together should be like evaluated and passed through a policy engine to determine whether or not you should gain access, and that you should like marry those three kind of seemingly separate concerns into a single decision point so that you can do more rigorous analysis on whether or not communication should occur. And so we think like if you are going to say that like considering all those components in your policy engine is important, it's probably a good idea for us to give that thing a name because we're going to talk about it a lot. And so the name we chose is Network Agent. It was an attempt to like kind of echo the idea of your browser is a user agent. It's a system that's working on your behalf with your like authorization. Might not be the best term, but it's what we picked. Maybe security context in retrospect might have been a bit less like fancy name, but probably a bit more clear on like what exactly we're talking about here. And so kind of the key idea here is that when you start digging into this, if we have user, devices, applications, we need to think about authentication and authorization. Interestingly, on the authentication side, you can authenticate each of these individually, and you probably should authenticate each of them individually. But when it comes time to do authorization, you should purposefully not like authorize devices or users separately. It's always this agent that you're coming back to write your authorization decisions. And interestingly, even more so is when you start digging into even that security context, like there's a time component here that's hidden in security context. So you want to, as much as possible, build networks where you are constructing the security context, authorizing it for now, and then throwing it away, and then the next like communication needs to go through that same policy engine again. And it's really neat, like this idea of having a network agent and writing authorization against it. It better captures what you see in a lot of like systems today where people are very rigorous in their security architecture. So an example I like to give is working at Stripe, where security is very important. I have different levels of access based on which device I am using, even though Stripe knows I am in fact who I say I am. So I can only check my email on my phone, but I can only write code, say on my laptop or something like that. And so that's like that idea of a network agent inside their policy engine making decisions. So another key idea here is if we're going to build this system that's like a big distributed system, it's changing all the time. We want to like grant it a lot of control of the control systems themselves. We really need to put in place like automation systems that we trust to actually operate the system, because it's unrealistic to imagine a system where we do like fine-grained authorization decisions and we're tasking like humans with reconfiguring every single device in the network. And so when you build these automation systems, really, if you take a step back, what are you doing? You are divorcing the enforcement systems, the configuration of those enforcement systems, from the control interface that you use to make changes to the policy in the system. And so then this automation system's job is really to take like this kind of centralized policy that humans have crafted and just always make sure that the infrastructure is conforming with that. And if something needs to change because the policies change, it has the autonomy to go and like make that change automatically. I think this is like a critical component of building a zero trust network and being successful with it, is you need to have that like separation and trust in your automation system. Because if you don't automate it, then humans being humans, we're naturally going to try to like minimize how often we have to make changes, but we don't really care that much if like machines go about making changes that we expect of them. So that talks a lot about like enforcement, but I think like zero trust networks aren't just about like enforcing rules or capturing someone trying to attack the network. There's also like these kind of like side benefits you get when you build these types of networks. And one of the biggest ones is like you get a much better visibility inside your network when you've kind of started building a zero trust architecture. A lot of companies, because they are configuring or constantly reconfiguring the infrastructure based on changes to members in the network, tend to put in place these sidecar infrastructure components to route all traffic through. A good example of this is Lyft has a proxy called Envoy that companies are starting to deploy more widely. And so Envoy is a way for you to set up like a mutual TLS service mesh. But as long as you're going to set up the infrastructure and route through it, you also get other benefits like logging of every request. You get operational benefits like circuit breaking technology that's independent of the application. So on the security side, if we had like pervasive logging for every network request, that sounds very attractive because if there ever is a situation where I need to analyze an incident, I've logged literally every request. I can go through that and use it to do forensics, or I could be a bit more proactive and use that as a way to do like risk analysis of my network. Another like kind of key thing when we talked with people is the importance of like starting early. And I think this all comes back to like the policy database that we're building up is like the key asset that zero trust networks need in order to be successful. And waiting till you're several years down the line and having already built a network without these concepts just becomes more and more painful. It's a lot easier to like kind of amortize this thing over time. And I think like even if you imagine some company saying, well, I could just automate like discovering everything once I have a system up and running. I think some of this value is also just like people understanding what is actually supposed to be occurring in their network. And not simply like saying, well, I can observe that it occurs, and therefore it must be allowed because it's already doing that. So, if you're starting out on a network and you recognize that the security is very important, you want to build a zero trust network, as soon as possible, you need to come up with good practices to, build this database and make sure that it stays current over time. Probably the best way to keep it current over time is to actually get it into the enforcement path, although that's not necessarily required. Maybe you could have some sort of like side database where you're checking like flows and actually reacting to changes and trying to like continually classify them. So what's the current state? If you are excited about zero trust networks, unfortunately there's just a lot of work right now. Most zero trust networks tend to be build your own. There are vendors that are starting to come out that try to take like a portion of the work and help you with that. But ultimately, this is like a big, complicated problem space that I don't know that there will ever be one person that you can just go and say, give me a zero trust network, and like they will secure everything for you. I think it's really just about picking good tools, oftentimes a lot of open source tools that you're familiar with, and applying them very rigorously through automation. And that's about it for me. I'm going to bring Evan back up. He's going to share with you some of the organizations and projects that are working on this type of stuff.
Thank you, Doug.
Yep.
Is this yours?
Mm-hmm.
Yeah. So it's a lot of stuff. Who's actually crazy enough to build these kinds of systems? Well, first, I mentioned before, you can kind of roughly split zero trust deployments into two categories. This client-side category for client access to enterprise resources, and then the server-side category for like service-to-service communication within a data center. And the distinction is made between these two different deployments for a couple of reasons, but mainly because clients behave a lot different than servers do. Clients tend to be wild. They do whatever they please. They ask weird things. Servers are a lot more predictable. You kind of know what they're going to do ahead of time. If they're not doing that thing, that's unexpected. And so because of this kind of fundamental difference, we tend to model the systems quite differently, whether you're talking about clients in the field or servers in the data center. So in terms of client-side implementations, we have companies like Coca-Cola, Mazda, and Google. And Google with their BeyondCorp implementation, of course, which is client-side. And Coca-Cola uses Zero Trust client-side network in order to enable like rapid provisioning of branch offices. IP addresses don't matter, locations don't matter, so when they want to turn up a branch office, it's as simple as calling Comcast or whatever the ISP is, plugging in a hotspot, and you're kind of off to the races. You don't have to worry about contacting the IT department and getting a tunnel set up and all this other stuff, And similarly, Mazda is using this technology for phone homes from their car fleets. The cars are rolling computers these days, and they have all this telemetry on board, and they do actually phone home over cellular, which is famously insecure networks. And so they use zero trust approaches in order to secure these kind of client callbacks to their cloud resources. So they use a technology called SDP to do this, software-defined perimeter, which is something to check out if you're interested in that. And of course, Google did this simply for raw security and scalability. It was partly done in response to some attacks that they saw, and also partly done because guess what? Like running these giant perimeter firewalls, fault-tolerant stuff is pretty hard to do, and it's pretty hard to do effectively, particularly at scale. And on the server side, we have companies like Lyft, Square, and of course PagerDuty. Most of these companies adopt for just raw security principles. PagerDuty being a minor exception, we adopted because of this multi-cloud, multi-region architecture that we had. And if you've ever used Docker Swarm under the covers has some strong zero trust principles in that it does MTLS everywhere and frequently rotates certificates, and the network is largely untrusted in a Docker Swarm cluster. But most of these companies have kind of rolled their own. As Doug mentioned, there's not really any kind of like give me a zero trust vendor, right? There are some commercial vendors, however, that are available for like various components or functions that you would normally find in a zero trust network. So Aporeto, Calico, and Illumio are working on zero trust problems in the data center or server-to-server problems. There's also a company named Edgewise which is working on similar problems. There's a company called CryptZone, Vitter, and Waverly Labs which are working on these client-side zero trust problems by way of this software-defined perimeter technology I was talking about, which the Cloud Security Alliance is currently working on. And then there's ScaleFT and Duo, which are also working on client-side technology, but kind of like a la BeyondCorp style, so the like BeyondCorp type approach to the problem. And all these vendors provide components which are useful in building a zero trust network, but there's still no end-to-end solution, and they're far from mutually exclusive. As Doug mentioned, I heavily doubt that there will ever be a vendor where you can just go buy a zero trust network because they're large and they're complex, and often they mix and match, and different things make sense for different sites and different deployments. So I wouldn't quite say that it would be reasonable to say like this vendor I can just make a contract with and they're going to give me zero trust. It's kind of more like has to be kind of well thought out and understood and applied to whatever use case you may have. So you take all this stuff together and it's not too hard to see. Hiding behind the perimeter alone is it kind of really undermines system security fundamentally, right? Because you let your guard down if you think the network is safe. The sad reality is the network is rarely safe. In fact, practically never safe. And the industry at large is moving towards this deep authentication and authorization, which is pervasive throughout your infrastructure. And they're doing this largely to compensate for holes in this perimeter architecture, which we see deployed even today still so often. And I think that the industry will eventually converge on this zero trust model where resources have to be directly protected themselves, and resource-to-resource communication must have end-to-end encryption and all of this kind of stuff, right? And we can already kind of see this happening today. And some of these products I mentioned before are more ambitious than others. They try to take various slices of the pie. But like I said, there's very unlikely to be a future where there's a single system or single vendor or product or piece of software which can cover kind of the whole pie, just because the problems that need to be tackled in order to achieve this reality are all very different from each other. There's not a single problem that you can focus on. But the end story of this is just a more secure system, which is actually more operable because of the high degree of automation and the freedom to move resources around, regardless of what the underlying network topology is a very powerful concept. So new things are happening every week. This is still all pretty new stuff. Our book came out like a few months back, and we worked on it for 2 years, and only now we're starting to see people like actually really try to address this problem and things popping up onto the market. But there's new developments pretty much every week in this area. So I do encourage you to kind of keep an eye out and an ear out because it's a very exciting time for this kind of technology. So if you're interested in hearing more, Doug and I will be here for a little while. We're happy to answer any questions, and thank you for having us. That's all we've got for today.
We do have time for questions. Please use the microphone again.
You want to come up, Doug? Come on.
Hello, thank you for a great talk. I just yesterday at Birds of a Feather session, was interested if you heard of Xenier.
Xenier. I have not heard of Xenier.
Zener. So it's not, as you say, there's like a lot of problems involved, but I just wanted to mention it because they did a demonstration. And as far as the automation side of the thing, they've got, the UI and so on, and they're just starting out, but a distributed firewall. So obviously, great for greenfield. If you have an existing infrastructure, then that's sort of the impossible to vendorize part of it, which I've confronted in my own consulting, or you have.
Is this the LinkedIn talk by chance?
It's related to that. It's very similar to what LinkedIn has, and the fellow who gave that talk was there as well.
Interesting.
And I just wanted to.
Yeah, we'll definitely check it. I'd like to catch you afterwards, actually.
Yeah,
if
definitely.
You don't mind hanging around. Yeah, thank you.
Hi, it's called zero trust model, but you need at least a trust model to bootstrap, no?
Yeah. So we were the wording and approach is very careful. If you actually look through the book, it's kind of ironic because it's named Zero Trust Networks, but the entire book is literally about managing trust. And so I think like kind of the way that we look at this is, when we say zero trust network, right? It's you're still trusting the systems and you're bootstrapping trust into the systems themselves, but you're building the systems in such a way where they manage trust so carefully that you're able to not place any trust on the network itself, the wires between these systems, right? So yes, there's like a lot of trust in compute systems, and we have to have this, otherwise what good is a computer if we can't trust the output that it's giving us? We wouldn't necessarily call it zero trust systems, but we call it zero trust networks because it's a systems architecture which allows you to remove trust from the network. Namely, do you trust the IP headers and these kinds of things? Does that make sense?
Thanks.
So this goes beyond just securing the pipes, and it's fantastic for an enterprise network. Now, part of the other part of a enterprise security is you're watching what's coming in and going out. So if you should get something rogue in the network, and I'm thinking of something like the Sony hack or something like that, do you have any type of packet inspection or anything for DLP?
You want to take that one?
Yeah, sure. I think like the companies that are doing this, like that's why Envoy tends to be a very attractive project for them, because basically all communication flows through Envoy and gives you like a centralized place to do analysis. You could definitely still do rolling packet captures and all the kind of similar security mechanisms for watching out for rogue activity. But hopefully, like digging through that will be a lot easier if you actually know what to expect in the network.
Yeah. To add to that, this is a common question I get: is if all the packets are encrypted, what do I do with my deep packet inspection stuff? What do I do with my IDS and IPS systems? And that's a very good question. I think that number one, we had a slide where we said all flows are expected, and they're expected because we have policy that explicitly allows these flows to exist. As soon as flows pop up which don't exist, either they're dropped or they're immediately noticed because there's no policy which describes them. So you can relatively quickly detect intrusion because these patterns start popping up which don't have policy checked in to capture them, right? So that's one piece of it. Another piece of it is that that visibility slide that Doug talked to. As flows traverse the network and systems communicate with each other, you drag them through these very strong authentication and authorization processes at every hop, and each one of those is able to throw off events, right? And so as things traverse the network, you get this really great visibility into it. So it's not so much that yes, you may lose some deep packet inspection as a result of the encryption that you're applying to the flows. However, you get to know at an application level very, very well what is occurring underneath the covers because each one of these kind of gates that you have to go through can be instrumented.
Very good. Okay, thank you very much.
No problem.
We've run out of time for more questions right now. Sorry, but they'll be around.
We'll be around in the back here.
We have a break right now. Next session starts at 11. Thank you for coming, everybody.
Thank you.